Hello, this is Mike Bernico, and this is my midterm demonstration presentation for EECE 6040, Advanced Microsystems Design. Once again, I'm doing the automated pet feeder for this course. The project objective, we're trying to design a one-time daily pet feeder that has touchscreen scheduling. This is meant to do like a lunchtime feeding of a pet. Assuming that a pet owner can do the morning and evening feedings when they're home from work. The project implementation will use a PIC24EP programmed with MPLab. We use a stepper motor to move the hopper. It'll use a vibration sensor to detect dispensing of food and magnetic sensors for positional feedback of the hopper. Most of the mechanical housing components will be 3D printed. A few of them are existing hardware parts. And factors that will determine success of this project from this point is entry of a schedule into the touchscreen, accurate control of the stepper motor through each of the hopper positions, proper response from the feedback sensors, and providing notifications of errors on the touchscreen should they occur. So from a top-level design, we start out, of course, with our PIC24EP with touchscreen built in, primarily for control and the processing of the controls to the outputs. Here in the red, we have the stepper motor driver that's used to translate the commands from the microcontroller into usable voltage levels to control both the direction and speed of the stepper motor. The vibration sensor here is actually replacing what was originally an optical sensor. The vibration sensor is placed in the field where food is dispensed, and the food actually rolls across the top of a bracket that the sensor is mounted to. Each vibration closes a loop, closing a pulled up pin to then be pulled low. And each time it's toggled, that's counted inside the software to ensure that we at least receive some dispensed food each time the hopper is turned. We have magnetic switches that will be used to detect the hopper position and just make sure that as we rotate from one position to the next, that the hopper is where we expect it to be. And lastly, we have a piezo buzzer that's used to indicate a warning in either dispensing of the food or when we are completely out of food, so that someone's not caught off guard realizing that there is no food left. From the project status, we'll start out with the hardware. As I mentioned briefly, that we changed from an optical sensor to a vibration sensor. This was mainly due to the fact that an optical sensor had such a narrow field of view that it was possible for dispense to occur but not be detected by the optical sensor. The vibration sensor being placed directly in the path of the food, the distribution of the food can't help but touch at least one part of the bracket that's mounted inside. I may remove the magnetic switches since I've actually found that the motor has very good positional accuracy when told to go from one position to the next. The need for a magnetic switch may simply exist to ensure that if for some reason the motor drags, that we are capable of reaching the position that we were trying to get to. And lastly, from a hardware point, I still need to 3D print a wall mount. My idea is still to have the touchscreen mounted onto that wall mount as well. So I'm waiting to work out all the details of if anything else needs to change with the hopper before making the final wall mount to hold the unit and the touchscreen. Current progress is that I have implemented the code to drive the motor to specific angles and locations, and that's caused by real-time clock and calendar interrupts. And right now, for the demonstration, as you'll see in the video, I've actually got it set to a 10-second interval just to avoid needless delay for the presentation, but I have been capable of controlling it up to the hour and day mark at this point. That leads us to one of the only issues I faced through this, and that's for a while I'd encountered the fact that the real-time clock it looked as if it was not working as expected, but it turned out that I was using an LED to monitor the interrupt, and the initial condition of the LED was the same condition that I told the LED to go to during the first interrupt phase. So every time the first interrupt occurred, I missed it, and it looked like things continued on correctly after the second interrupt. Once that was solved, the rest of my problems with the real-time clock seemed to go away. For next steps, I still need to work on developing routines to catch errors in dispensing. As mentioned previously, I still need to 3D print the wall mount, and I need to code and test the magnetic switches should they prove to be useful. From a scheduling perspective, things look like they're right on time still. If you compare the two schedules from left to right, the left is from the last design review, the right is the current plan. The change from an optical detector to a vibration sensor pulled in the design of code for that to the point that the code for that sensor is actually implemented, other than the error catching routine. Outside of that, it did push things further on the schedule, but the actual feedback sensor was meant to be later in the schedule, so really I've just shifted time around. But if we look to the current schedule, the items in yellow as opposed to blue are the items that did change in terms of sequence and what needs to be done. For the project demonstration, I actually have two videos. One is just a general overview of the hardware, taking things around to show connectivity and where things are mounted that can't be seen simply from the overhead view used for the operational demo. And the operational demo shows from start to finish of entering time into the touchscreen for the current time and alarm, and watching the hopper rotate and dispense. As far as the operation is concerned, it starts out with on-screen instructions for filling the unit and how to start things up for its initial position. And then you utilize touchscreen to set the current time, utilize the touchscreen to set an alarm time. Then the LCD will continuously display the remaining days of food left. It will continue to decrement that each time food is dispensed. And when there's no food remaining, it actually produces an alarm, an auditory alarm using the piezo buzzer, and produces a message on the screen that says you're out of food. The piezo buzzer sounds on a 10-minute interval, so it can't be missed, and is just annoying enough to make someone remember that it needs attention. For preliminary results, I have seen correct touchscreen responses in all my menus. I have successfully used the RTC interrupt at varying intervals, and I've seen correct rotation of the hopper, and I've seen the correct decrement of the food count as the hopper rotates. And lastly, here we have the PIC24's datasheet and datasheet errata, the programming 16-bit microcontrollers in C, as well as graphics, touch, sound, and USB, both from DeHasio. The PIC24 EP user's manual from Microelectronica, and the stepper motor controller, the A4988 datasheet from Allegro. I appreciate your time. Thanks for listening.